Now in this video lecture we will go through sizes of tetrahedral and octahedral void, right? And we will see how the size or the radius of these tetrahedral and octahedral voids relates to the size of the particles or the radius of the particles in packing, right? And in these calculations we would be deriving the relation between this radius of the voids and the radius of the particles in packing, that is the bigger spheres, right? In the previous lecture we have drawn the bigger spheres which occupy the space, right? And the smaller spheres which represents the void between the particles or the spheres, right? So now in this video lecture we will see that, and in the previous lecture we have already talked that the radius small r, right, of tetrahedral void is equal to 0.225 radius of the sphere or the radius of the particle in packing, right? And the radius r of octahedral void is equal to 0.414 times the radius of the particle in sphere, or the radius of the radius of the particle in packing, or the radius of sphere, right? Now if you look at the diagram, right, if you look at this diagram, these four spheres represents the four particles, right? And these four spheres represents the four particles in packing, and this small sphere which is between these four spheres represents a void, that is the empty space, right? And in this diagram since this board is two-dimensional, so there are two particles or the two spheres, one above this and one below this layer, right? So this is a system of six spheres, right? And a particle and a void space, a void or empty space, right, that is formed by six particles is your octahedral void, right? So using this diagram we will find the relationship between the radius r of octahedral sphere and the radius r of this bigger sphere, which is the particle in packing, right? And we will prove that this relationship small r is equals to 0.414 r of r, that is the radius of the sphere or the particle in packing, right? So we'll just prove this. And in the previous video lecture we have talked about ionic solids, and we said that in ionic solids we have anions, right, and cations. These anions will form the particle, right, in packing, right? That is, these particles, bigger particles, will represent anions, right, in your ionic solids, because ionic crystalline solids are also three-dimensional, right? So particles, that is the ions of these ionic solids, cations and anions, would be arranged in three dimensions, right? So these anions, because they are bigger in size, right, than cations, anions will go in packing, right? And these cations will go in voids, in empty spaces, because cations are small in size, right? And the second thing is these cations will go in voids, right? And if cations are smaller, then they will go into, or they will form tetrahedral voids, they will go into tetrahedral voids. And if cations are bigger, they will go into your octahedral voids, right? So if these are small, they will go into tetrahedral voids, right? And if they are bigger, then they will go into octahedral voids, right? And this is the maximum size of the void, right, that is present in the close packing, right? Close packing of particles in 3 dimensions. And if the particle, or I'm sorry, if the void, right, if the void is bigger than this, then the packing is no more close packing, right? So we say that for close packing, maximum size of void is equals to maximum size of the void, that is R, is equals to 0.414 of the radius of the particle in packing, or the radius of this bigger sphere, right? So just remember this about ionic solids, that anions are bigger, so they will form particles in packing, and cations are smaller, so they will go in voids. And if cations are bigger, then they will form octahedral voids, or they will go into octahedral voids, and if they are smaller, they will form tetrahedral voids. Now let's prove this relationship using this diagram, right? Now this is a sphere, small sphere, that represents a void, octahedral void, surrounded by these small spheres. These, you can see here, small spheres. Now this is an octahedral void, so this must be surrounded by 6 spheres. So there is a one sphere above it in 3 dimensions and one sphere below it, right? So it's a system of 6 sphere, right, and a one void between these 6 sphere, which is an octahedral void. So let R be the radius of octahedral void, right? This would be R. R is the radius of this octahedral void, right? And R be radius of sphere. Sphere represents the particle in packing, right? Now we'll apply Pythagoras theorem in this triangle, right? If we join the center of these spheres and this with the center of this void, right, then it forms a triangle, right? And this is a right angle. If we apply Pythagoras theorem in this triangle ABC, we get this BC square is equals to AB square plus AC square, right? And we know that this AB is the radius of this small sphere, small r, and from this point to this point, this is the radius of this bigger sphere, capital R. So we have AB, same is with AC. So AB is equals to AC is equals to R plus R, right? R is the radius of this small sphere, plus this AB is equals to this plus this. So small r plus capital R, right? This. If we apply now Pythagoras theorem, this Pythagoras theorem is applied in this triangle. BC square is equals to AB square plus AC square. Now we know that BC square is your R plus R. If you look at this, R plus R, these are the center of these two spheres, right? So BC is equals to R plus R whole square is equals to AB square is your R plus R square plus AC is your R plus R square, right? So this is your 2R square is equal to 2R plus R square, right? So this is your 4R square is equals to 2R plus R square. 2R square is equals to R plus R, right? So R plus R whole square. So if we take under root of both the sides, taking under root of both the sides, you get root 2 R is equals to R plus R, right? Now if you bring this R here, root 2 R minus R is equals to R. Therefore taking r common, it would be root 2 minus 1 is equals to r. And this root 2, the value of root 2 is 1.414 minus 1 is equals to r. Therefore this 1.414 minus 1 is your 0.414. The value of root 2 is 1.414. So this is your 0.414 of this capital R is equals to small r. Hence proved. Right? This derivation proves this relation, that the radius of octahedral void, here we have taken the octahedral void as small r, right, and the capital R as the radius of the particle, that is the bigger sphere, right. And we applied Pythagoras theorem in this triangle, right, and just remember that this is your 2r, right, r plus r, and this is your r plus capital R. This is similarly here small r plus capital R, right. If you apply Pythagoras theorem and solve it, you will get this, right. So this is proved, hence proved. So now let's look at this proved your octahedral, the relationship of octahedral void, right, and the size or the radius of the sphere. Now let's look at the other one, right. The other one is your tetrahedral void, this relation. Now we will prove this relation, right. If we take the diagram like this, right, like this, right. So this is a cube, right. So A, this is your B, and this is your D, right. This. And this is your C, and this is the center of this cube, right. And here let's say this is your E, right, and every corner we have a particle, right. And let's say the center of this cube, this center represents a void, right. Let's say this is a void, right. Now we have to prove this relation, that is, we have to prove that R is equals to 0.212, I'm sorry, 225 of capital R. So if this is the void, let's say the radius of this void be small r, right, and these represents particles. So let the radius of these particles, all these particles in corner be capital R, right. And so we go ahead and join these, right. Similarly we will join this point as well, right. Now if you look at this diagram, this point A and B that we joined, right, this represents the face diagonal of this face of this cube. This is the one face, this is one face of the cube, and this is the face diagonal, right. And we have joined this as well, right. And this represents the void, right. Let R be radius of void, and capital R be the radius of particle at corners, right, particle which is a sphere. And this is an open diagram, right. And if we draw a closed packed diagram, with it in closed packed diagram, all these particles must be touching one another, right. So this and this will touch one another, this and this will touch one another. Similarly this will touch this void, and this will also touch this void, right. Now in the triangle ABC, right, now let the edge of this or the side of this cube is A, right, here also it's A, right, this is the side of the cube, right. Now in the triangle ABC, right, if you apply Pythagoras theorem in the triangle ABC, right, let's apply Pythagoras theorem in this triangle ABC. In triangle ABC we have, if this is the right angle, then AB square is equals to AC square plus BC square. Therefore AB is equals to AC square plus BC square, right. Now we'll look into the bigger triangle ABD, right. In the triangle ABD we'll apply the Pythagoras theorem in the triangle ABD, but before that let's find what is AB, right, and what is AC and BC. This is the side of the cube AC and BC, so both are same A, right. So we have AC is equals to BC is equals to A, which is the side of the cube, and this AB, if you look in closed pack diagram, these both touch one another like this. This is how these two particles in actual touch one another. They are not this far, right. In closed packed structure, these two particles touch like this, and we said that the radius of these spheres is capital R. So this is capital R and this is your capital R, right. So this AB is this distance AB, right. This represents your AB. Let me just draw it a little bigger. This and this, right. This is your A, this is your B, this is R, and this is R, right. This AB represents the center of these two spheres. This is R, this is R. Therefore, AB is equals to 2R. Right, now let's put the values here. The value of AB is 2R. AC is A, so this would be A square plus A square is equals to under root 2A square. So 2R is equals to under root 2A. Right. So this is your R is equals to under root 2 upon 2A. Right. This is your under root 2 upon A. So if you just multiply both the sides with under root 2, it would be under root 2 upon under root 2. This would be equal to under root 2 into under root 2 is 2. This is A is equals to A upon under root 2. So this is the relation between radius of the sphere and side of the cube. Right, R equals to A upon under root 2. Right. Now we'll consider another right angle triangle, which is your ABD. Now we'll see this triangle ABD. Right. Now consider triangle ABD. Right. This we'll consider it right angled at here at B, right, which is right angled at B. Therefore, this AD square is equals to AB square plus BD square. Right. Therefore, AD is equals to under root AB square plus BD square. Right. Then your AB is again your 2R, right, and BD BD is your A, which is your A square, right? So we'll put the value of AB, right? AB as, we'll put the value of AB as your, from here we will calculate the value of AB, right? AC is equals to BC, which is your A square, right? AC square, A square plus A square. So therefore AB, which is, we found here, AB is equals to 2R. So this would be under root 2A. This AB is, the value of AB is, from this relation, from this triangle, it's under root 2A. This is would be under root 2A whole square plus BD is your A square. So AD is equals to, this is your, this would be your 2 square plus A square. It would be 3A square under root 3 A square, which is under root 3 dot A. Therefore AD is equals to under root 3 dot A, right? This is the value of AD. Now we have the value of AD, right? Now the body diagonal AD, if you will find the value of AD is this, right? The value of AD would be, if this is the particle, right? If you look at it here, this is how it looks like. This is your A particle, the center of A, and this is your, this void will also touch this particle and this particle. Let's draw it little small, and this a little bigger. So this is your R, this is your small r, then again this is your small r, this is your R, right? This is how this AD will look like, AD, right? So this R plus R, the R is the radius of small sphere or the void, so R plus R is your 2R plus R, the radius of the second particle over here. This is your R, therefore this is 2 plus R plus R. This is the value of, this is your AD, right? So value of AD is your 2R plus R, right? So let's put the value of this AD here, 2R plus R is equals to root 3A, right? So R plus R would be root 3 upon 2. Therefore, this R plus R is equals to root 3 upon 2 dot A. Right? This is the first relation that we have got, right? This is the second relation, I'm sorry. The first relation that we got was your R is equals to A upon root 2, right? This one, AB is equals to, this AB is equals to root 2A, so we have put all the values here. The R is equals to A upon root 2. This was first relation and this was second relation. So if we divide this by this, right, from first and second, R plus R, you divide it with this equation, divide this with this. Sorry. Plus R upon R is equals to root 3 upon 2 dot A upon root 2. Root 3 upon 2 right? So this would be root 3, a and a will cancel, 2 and 2 will cancel. This would be root 3 upon root 2, right? This is how it will come, the root 3 upon root 2. And if you will solve this further, 1 plus r upon r is equals to root 3 upon root 2, right? Now we'll bring this here, we'll subtract it, right? When we will subtract it, we will get r upon r is equals to 1 minus root 3 upon root 2. So this would be root 3 minus root 2 minus root 3 upon root 2, right? So r upon r I'm sorry, this is little wrong. What we will do is this r upon r is equals to root 3 upon root 2. This minus 1 will go here, minus root 3 minus root 2 upon root 2, right? So small r upon capital R, right? If you will calculate the value, if you put the value of all these, this will come out to be 0.225, right? This is the value of this would be 0.225. Therefore r upon r is equals to 0.225, right? This r will go here, therefore r is equals to, small r is equals to 0.225 r. This proves this relation. The radius r of tetrahedral void is equals to 0.225 of r, which is your particle in packing, right? So now we have proved both the relations. I'll just repeat this. We'll just summarize this one. Right here, first we have considered this triangle. We applied Pythagoras theorem in this small triangle, right? We got an ABC, AB square is equals to AC square plus BC square. AC and BC both are A, right? So this AB square would be root 2A, right? So we will put the value of all these values here. AB would be equal to, this AB is 2r, like we have calculated here. These pairs are touching one another, so this is 2r. We put the value 2r, this, right? This will come out to be r upon a upon root 2. First relation. Second relation we will get from another triangle, this bigger triangle, which is considered a right angle at point B, right? So AD square is equals to AB square plus BD square, right? So we'll put the value of AB, right? The value of AB, right? And the value of BD. BD is A square, BD is A, so it will be A square, and AB is your root 2A, right? This is the value of AB. The value of AB is taken from here. This is root 2. So this will get the value. AD is calculated from here. AD is this. So this void must be touching this and this, right? So this is your AD is equals to 2r plus r. We'll put this value here and we get this. Then we will divide this with this, right? So after solving we will get this, hence proved. I hope this is clear. Both these relations are clear, right? Thanks.